Good morning, students. Now, the next part of chemical kinetic is obtain exponential form of integrated rate law. The integrated rate law of first order reaction is given by K is equal to 2.303 upon T log to the base 10 A0 upon AT. K is equal to 1 upon T natural log A0 upon AT. So, therefore, natural log AT upon A0 is equal to minus KT. Okay. So, by taking antilog of both sides we get concentration of AT upon concentration of A0 is equal to e raised to minus KT. So therefore AT is equal to A0 e raised to minus KT. Okay. So the above equation is called, this equation is called exponential form of first order reaction. Okay. Now the next part, state the unit of rate constant of first order reaction. What is the unit of rate constant K of first order reaction? The integrated rate law is K is equal to 2.303 upon T log to the base 10 A0 upon AT. Because log to the base 10 A0 upon AT is unitless. Log to the base 10 A0 upon AT does not having unit. It is a unitless quantity. Therefore, the dimensions of K will be per time. So, therefore, unit of K for first order reaction is per time. So, per time or per minute or per hour. Okay. The unit of rate constant for first order reaction is per second or per minute or per hour. Okay. Next point is define half life. Half-life of a reaction, it is defined as the time required to reduce the concentration of reactant to one half of its initial value. It is known as half-life. Now, what is the exactly definition? The half-life of reaction is the time required for the reactant concentration to fall. The time required, the half-life of reaction is the time required for the reaction concentration to fall to one half of the initial value, to one half of its initial value. This is known as half-life of the reaction. Once again, what is half-life? The half-life of reaction is the time required for the reactant concentration, time required for the reactant concentration to fall to one half of its initial value. This is known as half-life of reaction. Radioactive possesses follow the first order kinetics. Okay. So now the derivation is there. Derive the relationship between, one derivation is there, half-life period. Derive the relationship between, this is very important derivation. Okay. So derive the relationship between the rate constant and half-life of first order reaction. What is the relationship between rate constant and half-life of first order reaction? The half-life of first order reaction is independent of initial concentration of reactant. Half-life of first order reaction is independent of initial concentration of reactant. So we have to derive the derivation of half-life period. The half-life period it is indicated by T half. So the integrated rate law for first order reaction is given as, what is the derivation of integrated rate law for first order reaction? K is equal to 2.303 upon T log to the base 10 A0 upon AT. This is the mathematical expression of integrated rate law for first order reaction. What is integrated rate law? The equation which are obtained by integrating differential rate law and which gives direct relationship between initial concentration of reactant, that is concentration of reactant, and time. It is known as integrated rate law. Okay. So the integrated rate law equation is given as K is equal to 2.303 upon T log to the base 10 A0 upon AT, where A0 is the initial concentration of reactant at time T is equal to 0. The initial concentration of reactant falls to AT. The initial concentration of reactant A0 falls to AT after time T. If A falls to AT at time T after the start of reaction, the time required for A0 to become A0 by 2, it is denoted as T half. Initial concentration of reactant falls to AT. So therefore, the time required for A0 to become A0 by 2 is denoted as T half, and this T half is known as half-life period. So therefore, AT is equal to, if AT is equal to A0 by T, then T is equal to T half. So substituting these values in integrated rate law equation for first order, we get K is equal to 2.303 upon T half log to the base 10 A0 upon AT. What is AT? A0 by 2. This is value of AT. At half life T half, at T half, T is equal to T half. What is the value of AT? AT is equal to A0 by T, A0 by 2 at time T is equal to T half. So therefore, K is equal to 2.303 upon T half log to the base 10 A0 upon A0 by 2. So A0 will get cancelled. We get K is equal to 2.303 upon T half log to the base 10 2. Substituting the value of log 2. What is log 2? Characteristic of 2 is 0 and log of 20 is 3010. So therefore, substituting the value of log 2, K is equal to 2.303 upon T half into 0.3010. So therefore, multiplication of 2.303 into 0.3010 is 0.693. What is the value of 2.303 into 0.3010? It is equal to 0.693. So therefore, K is equal to 0.693 upon T half. So therefore, T half is equal to 0.693 upon K. So this is the mathematical expression for half-life for first order reaction, and this is very important derivation. Very important derivation. Okay. Now next, how is half-life for first order reaction related to initial concentration of reactant? How is half-life of first order reaction related to initial concentration of reactant? It is independent of initial concentration of reactant. The half-life of first order reaction is independent of initial concentration of reactant. Okay. Now, next question, graphical representation. Identify the order of reaction based on following graph. So, first graph is graphical representation. The graph is plotted against concentration of reactant at time t and versus time. So, graph of half-life period of first order reaction is, first graph, graphical representation for first order reaction, half life period of first order reaction. It indicates that the concentration, this is the concentration AT versus time graph. This graph represents the graph of concentration AT versus time t plot for a first order reaction. Okay. Now next one, how will you represent first order reaction graphically? How will you represent first order reaction graphically? So there are three graphical representation for the first order reaction. First one is the differential rate law for first order reaction is the differential rate law for first order reaction. Consider the reaction A gives product P. For this reaction, the differential rate law is rate is equal to minus dA upon dt. Rate is equal to minus dA upon dt is equal to K into concentration of AT plus 0. So this equation is of the type y is equal to mx plus c. So what is y? Minus dA upon dt is y. What is k? What is m? K is known as m. K is constant. And what is x? AT is known as x. And what is c? C is equal to 0. So the equation is of the form y is equal to mx plus c. And by plotting the graph, a plot of rate versus AT is a straight line passing through the origin. This is the graphical representation. When a graph of rate and initial concentration is plotted, it gives a straight line graph passing through the origin, and the slope of this graph gives the value of K. By plotting this graph, which graph? Rate of reaction versus concentration, initial concentration of reactant, that is AT. As we plotted a graph of rate of reaction versus concentration AT, it gives a straight line graph passing through the origin, and the slope of the graph is a straight line, and it gives the value of, slope of the graph gives the value of K. Okay, so this is the first graphical representation. Now second graphical representation, the integrated rate law is, what is the integrated rate law? K is equal to 2.303 upon T log to the base 10 A0 upon AT. This is the integrated rate law for first order reaction. Now arrangement of this reaction, on rearranging this equation, it gives, on rearranging the equation becomes Kt upon 2.303 is equal to log to the base 10 A0 minus log to the base 10 AT. On rearranging the above equation, we get Kt upon 2.303 is equal to log to the base 10 A0 minus log to the base 10 AT. Hence, log to the base 10 AT is equal to log to the base 10 AT is equal to minus K upon 2.303 into T plus log to the base 10 A0. This equation is of the type y is equal to mx plus c. What is y? Y is equal to concentration log to the base 10 AT. What is m? K upon minus K upon 2.303. This is m. And what is x? T is equal to x. And what is c? Log to the base 10 A0. It is known as c. So this equation of the straight line. This equation is of the straight line. So a graph of log to the base 10 versus t is plotted. When a graph of log to the base 10 AT is plotted against time, gives a straight line with slope, negative slope. It gives negative slope minus k. The slope of the graph gives the value of minus k upon 2.303 and y-axis intercept as, what is the interception on y-axis? The interception on y-axis indicates that log to the base 10 A0. This is the interception on y-axis. Okay. This is the second graphical representation. Now the third graphical representation. Rearranging integrated rate law equation we get. By rearranging integrated rate law, what is the integrated rate law? K is equal to 2.303 upon T log to the base 10 A0 upon AT. On rearranging this equation, we get log to the base 10 A0 upon AT is equal to KT upon 2.303. So here y is equal to log to the base 10 A0 upon AT. M is equal to K upon 2.303 and X is equal to T. Okay. So the equation has a straight line form. This equation by plotting the graph of log to the base 10 A0 upon AT versus time, we get a straight line graph. The equation has a straight line form. Y is equal to mx. Hence, the graph of log to the base 10 A0 upon AT versus time is a straight line passing through the origin. Okay. So this is the graphical representation of first order reaction. So there are totally how many graphs for first order reaction? 3 graphs. Okay, this is not the graphical representation for first order reaction. This graphical representation represents half life period. Okay, so this is the first graphical representation for first order reaction. This is the second graphical representation, and this one is the third graphical representation. Okay, now next part, give 2 examples of first order reaction. So decomposition of hydrogen peroxide is an example of first order reaction, and decomposition of nitrogen pentoxide N2O5, it is the second example. So twice of H2O2 liquid gives twice of H2O liquid plus O2 gas. This is the first example of first order reaction, and from this reaction we get rate is equal to K into concentration of H2O2, because of for this reaction rate depends on 1 mole of H2O2. Okay. Second reaction, twice of N2O5 gas gives twice of NO2 plus O2. Here 2 is not there. Okay, so we have 2 here. So twice of N2O5 gas gives twice of NO2 gas plus O2 gas. So therefore for this reaction, what is rate? The rate is equal to, for this reaction the rate of reaction depends on 1 mole of N2O5, but here in this reaction 2 moles of N2O5 is given, but rate does not depends on 2 moles of N2O5. So therefore experimentally it is found that rate of reaction depends on 1 mole of N2O5. So therefore rate is equal to K into N2 concentration of N2O5. Okay, this is the examples of first order reaction. Next question is, derive integrated rate law for first order reaction. Derive the integrated rate law for the first order reaction. A gives B plus C. In terms of pressure, integrated rate law for first order reaction in terms of pressure. Okay. Now for the gas phase reaction, consider the gas phase reaction. For the gas phase reaction, A gas gives B gas plus C gas. Here A is reactant, B and C are products. So let initial pressure of A is Pi. Pi is the initial pressure of A that decreases by X. Within initial pressure of A is Pi that decreases by X within the pressure of reactant A within time. So initial pressure of reactant A is Pi and this pressure decreases within time. Okay. Now here pressure of reactant A at time t is pressure of reactant A, PA, at time t is equal to PA is equal to Pi minus X, because of the initial pressure of reactant decreases by factor X. So the initial pressure of A decreases by X within time. Okay. So therefore pressure of reactant A at time t, Pa is equal to Pi minus X, called it as equation number 1. The pressure of the product B and C at time t, product C, the pressure of product B and product C is X. The pressure of product B and C is PB and PC, and that is nothing but X. What is pressure of A? PA is equal to Pi minus X. This is equation number 1. Now what is the pressure of product B and C? PB and PC are the pressure of product B and C there, and that is equal to X. So therefore total pressure at time t is the total pressure of reactant and product at time t is given by P is equal to summation of pressure of reactant and product. Summation. So therefore summation of A, pressure of A, summation of pressure of B and pressure of C. So pressure, total pressure, it is indicated by P. P is equal to Pi minus X. This is the pressure of A, plus X, this is the pressure of B, and plus X, this is the pressure of C. So therefore Pi minus X plus X plus X, it gives total pressure. P is equal to Pi plus X. Hence X is equal to, what is the value of X? X is equal to P minus Pi. This is equation number 2. Okay. So pressure of A at time t is obtained by substitution equation 2 in equation 1. Substituting equation 2 in equation 1. Substituting the value of X in equation 1. So what is X? X is equal to P minus Pi. So therefore we get Pa is equal to Pi minus into bracket P minus Pi. Pa, substituting the value of X in equation 1 from equation 2, we get Pa is equal to Pi minus into bracket P minus Pi. So therefore by opening the bracket we get Pa is equal to Pi minus P plus Pi. So therefore plus Pi gives 2 Pi. So therefore Pa is equal to 2 Pi minus P. Okay. So integrated rate law turns out to be, the integrated rate law turns out to be K is equal to 2.303 upon T log to the base 10 A0 upon 80. This is integrated rate law equation. So by substituting the value of A0 and 80 here, A0 is equal to Pi. The concentration is now expressed in terms of pressure. Here concentration are expressed in terms of pressure. So PA0 is equal to Pi and AT is equal to Pa. And what is Pa? Pa is equal to minus 2 Pi, sorry, 2 Pi minus P. So this is AT and A0 is Pi. Substitution this values in equation 3 we get K is equal to 2.303 upon T log to the base 10. A0 is Pi and AT is 2 Pi minus P. So P is the total pressure of the reaction mixture at time T. So this is the integrated rate law for first order reaction in terms of pressure. This is also very important. Okay. Now examples are there. First example, half-life period. On the basis of half-life period and integrated rate law equation. So the half-life of first order reaction is 990 seconds. If the initial concentration of reactant is 0.08 mole per decimeter cube, what is concentration? What concentration would remain after 35 minutes? So what are the values are given here? Half-life period of first order reaction is given, that is T half is given 990 seconds. So first of all calculate the value of K. So what is the formula of K? K is equal to 0.693 upon T half. So K is equal to 0.693 upon 990 second. So therefore on calculation we get 0.693 divided by 990, it gives 7 into 10 raised to minus 4 per second. Okay. So therefore the integrated rate law equation for first order is K is equal to 2.303 upon T log to the base 10 A0 upon 80. A0 is 0.08 mole per decimeter cube. We have to calculate 80. T is, what is time? Time is equal to 35 minutes. We have to convert this time into second. So 35 minutes is equal to 35 into 60. 1 minute is equal to 60 na? So 1 minute is equal to 60. So therefore 35 minutes is equal to 35 into 60, that is 2100 second. So substituting the value of A0 and time, we get log to the base 10 A0 upon 80 is equal to kt upon 2.303. K is 7 into 10 raised to minus 4 per second. T is 2100 second and divided by 2.303. So this calculation gives 0.6383. This value gives 0.6383. By taking log on right hand side, we get anti-log. Log on placing on right hand side, it gives anti-log. So therefore a0 upon 80 log to the base 10, a0 upon 80 becomes a0 upon 80 is equal to anti-log of 0.6383, and the anti-log of 0.6383 is 4350, and because of 0 it gives 4.350. Okay, so this is value of a0 upon 80. Now we have to calculate 80, so therefore 80 is equal to a0 upon 4.35. So therefore 80 is equal to a0 is 0.08 divided by 4.35, and it is 0.0184 mole per decimeter cube. So this is the value of 80. Okay, this is the first example. Second example, in a first order reaction, 60% of the reactant decomposes. How many percent of reactant decomposes? 60% of the reactant decomposes in 45 minutes. Calculate half-life of the reaction. So, if suppose if the concentration of reactant are given, you are given the concentration in terms of percentage, then initial concentration of reactant is 100%. Suppose you are given the concentration of reactant in terms of percentage, then take initial concentration of reactant, that is 100%. So therefore A0 is equal to 100% and 80 is equal to how many percentage are decomposes? Out of 100%, 60% get decomposed. So therefore how many percentage of 80 remains unreacted? 100 minus 60, that is 40% of 80 remains unreacted. So therefore the concentration of initial concentration of A is equal to 100% and 80 is equal to 100 minus 60, that is 40, and time is given, it is 45 minutes. So substituting these values in the above equation, we get K is equal to 2.303 upon T log to the base 10, 100 divided by 40. 100 means A0 is 100 and 80 is 40. So therefore 2.303 upon 45 log to the base 10, 100 divided by 40, that is 2.5. So 2.303 upon 45 log of 25 is 3979 and characteristic is 0. So therefore 2.303 upon 45 into 0.3979, that gives the calculation, the simplification of this gives 0.0204 per minute. Okay, so we have to calculate half-life period. What is the formula of half-life period? T half is equal to 0.693 upon K. What is K? 0.0204. This is K. So therefore 0.693 upon 0.0204 per minute. So it gives 34 minutes. Okay, this value gives 34 minutes, the value of half-life period. Okay, third problem is following data were obtained during the first order decomposition of SO2 sulfuryl chloride SO2Cl2 at the constant volume. So what is the reaction? SO2Cl2 gas gives SO2 gas plus Cl2 gas. Time is given in terms of per second. Time is given per second. At 0 time, what is total pressure? 0.5. And at time 100 second, what is the pressure of reactant is 0.6. So calculate the rate constant of the reaction. So what is the formula of first order reaction in terms of pressure? K is equal to 2.303 upon T log to the base 10 Pi upon 2 Pi minus P. So Pi is initial pressure of reactant is 0.5 at 0 time, and the pressure of reactant after time T is 0.6 bar. Pressure of reactant after time T is 0.6 bar. So therefore substituting these values, Pi is equal to 0.5 bar, P is equal to 0.6 bar and T is equal to 100. Okay, so therefore K is equal to 2.303 upon 100, that is time in second, log to the base 10 Pi is 0.5 bar divided by 2 Pi 2 into 0.5 minus 0.6. So 0.5 into 2, that is 1. 1 minus 0.6, that is 0.4. So therefore 2.303 upon 100 log to the base 10 0.5 divided by 0.4, and the calculation of this all the factor we get the value of K, that is 2.23 into 10 raised to minus 3 per second. Okay, so these are the example based on integrated rate law equation. Okay, thank you.